Welcome back. So we had concluded solar cells discussion in the last lecture, if you recall, the various properties and performance matrices of solar cell. Now we will discuss from today photodetectors, which are very similar to solar cell, but slightly different in some functionalities. You will see there are very subtle differences between solar cell and photodetectors. And photodetectors can of course operate in different wavelengths. You want to detect wavelength of different, light of different wavelengths, unlike solar cell where the spectra is fixed, that is the sun spectra, right. And photodetectors can also be photovoltaic, that means they can also give you electricity without applying any voltage when you shine light, but they are not necessary to give you good amount of electricity or to generate power out of that, okay, unlike solar cell. So you don't connect a load, for example. There are many things that are important for photodetectors. The reason I am telling you is because photodetectors are like sensors, and sensors are everywhere in the around the world. All the increasingly important fields like IoT and all other sensing technologies, they need these sensors, and photosensors or photodetectors are important for a large range of strategic, civilian, commercial applications. You may not be knowing it, but there are so many applications that you are actually using infrared sensors, and now they are wearable UV sensors and so on. Okay, so we'll start sensors today, sensors today. In the next couple of lectures, we'll try to finish up photodetectors so that we can start LED. Okay, these are optoelectronic part of the course under the syllabus. Okay, so we'll come to whiteboard here, and we'll start with photodetectors or photosensors. We will only consider semiconductor photodetectors, which means there are other kinds of non-semiconductor based photodetectors also, but we will not discuss those. Non-semiconductor based photodetectors would include something like vacuum tubes or some photomultiplier tubes and all. We don't want to discuss that. We will only discuss semiconductor photodetectors. And unlike solar cells, which have to be PN junction with a built-in potential, so photodetectors need not necessarily be in a PN junction. It may not be a PN junction, it can be just an N minus or an undoped silicon also, can be a solar cell, can be a photodetector. The difference stems from the fact that a photodetector basically, you have light that falls, right. You have light that falls, light of different wavelength, whatever you want, and you want to convert that into electricity. Not for power generation or power harnessing, but you want to sense. You have light that falls and you want to sense that light. So you and the photodetectors will convert that into electricity. So by the magnitude of that electricity, you can find out the intensity of the light that is falling. Of course, the material will be sensitive to only a particular range of wavelength. So you want to detect some particular range of wavelength. So you can choose a material of the appropriate band gap, for example. This electricity that you get should ideally is very small, and you don't that's because it has to be a very sensitive photodetector. You should be able to detect even faint light, okay, of any wavelength. And photodetectors, I told you, need not be necessarily PN junction. It can, you may or may not apply bias here, depending on the geometry of the photodetector. You may or may not apply bias, unlike solar cell where you definitely don't apply bias yourself. It will self bias for depending on the load. And in photosensors, you may or may not apply bias, which means it may be photovoltaic in nature or it may not be photovoltaic in nature. Okay, so in short, photodetectors take light and convert them into electricity. Okay, light up and when I say they take light and they convert into electricity, you please remember that the band gap of a semiconductor will decide which wavelengths it will absorb. So the wavelengths that it can absorb will be Hc by Eg less than equal to this, right. Photons of energy. So you have photons whose energy h nu is greater than band gap will only be absorbed and probably give you electricity. Okay, so if you have a band gap of 1 electron volt, you cannot absorb a photon of say 2 micron wavelength because it will pass through the that thing. So depending on what wavelength you want to detect, you need a band gap appropriately. You want to have the band edge at that wavelength or less more wavelength than that. So when I say photodetectors, it need not be only visible. Visible has all these red, yellow, green, blue and so on. It can also mean infrared. It can also mean UV. Infrared and UV are not visible to our eyes. We cannot detect infrared or UV, but there are sensors, photodetectors that can detect infrared and UV. UV also has many parts: UVA, UVA, UVB, UVC. We can come to that later. Different categories. I also have many categories like near infrared, mid infrared, and far infrared. Of course, these are not visible to our eye. They have a lot of military and other applications. Lot of Commercial application, lot of security, strategic applications, lot of biological, medical applications also, these infrared detectors. Okay, these are not visible to our eye. So you, depending on the wavelength that you want to detect, you will have a semiconductor of appropriate band gap that you are aware of. For example, if you want to detect an infrared signal of say 5 micron, then your band gap has to be, you know, HC by 5 micron. That will give you the band gap. It will be very small, maybe 0.1, 0.2 volt or so on. So you will need a very narrow band gap material. Suppose you want to detect a UV wavelength of 300 nanometer, that is UV, then you will need HC by 300 nanometer. Okay, it will probably be around 4.7 electron volt or so. So that is very large band gap material. So you need a large band gap material for UV detection, a small band, very narrow band gap material for maybe IR detection and so on. Okay. So I mean, of course, but you remember that silicon, for example, silicon has a band gap of 1.1 eV, which means it can actually detect signals whose photons or light whose photons are have energy more than 1.1 eV. For example, if you want to detect a UV light, if you want to detect a UV light of 300 nanometer whose band gap, you know, you said the band gap corresponding to that should be 4.7, 4.5 eV, but silicon's band gap is 1.1 eV, which means silicon also can absorb the photon of 4.7 eV. You see my point? So silicon has this band gap EC eV and this is 1.1 eV, but if a photon comes, if a UV photon comes whose wavelength is 300 nanometer or whose energy is 4.5 eV, then that 300 nanometer photon or 4.5 eV photon will also get absorbed in silicon and generate electron hole pair. Of course, there will be much higher energy electron hole pair. Some fraction of that may be able to come out as, you know, as electricity. Okay, so you can actually use silicon also as a detector in UV, but the problem is that silicon will also detect all the wavelengths, all the energy of the all the photons with energy whose energy is more than 1.1 eV. Malab, silicon will also absorb visible. It will absorb green, you know, yellow, red, near infrared, UV, everything it will absorb. So you cannot selectively say whether a light that you are detecting is only from UV 300 nanometer, because silicon will also detect visible. Say visible green, blue, yellow, all their photons are energy more than 1.1 eV only, which means silicon will not be selective to UV. So silicon will absorb everything from its band gap upwards. So you will not know if the photon you are detecting is only for UV or is it for, you know, or visible or something. So that kind of things are there. It depends on application. Of course, we will come to all these things. So now before we go into the working of devices of the photo detectors, we will start understanding the important figures of merit. Figures of merit of photo detector, like what are the important parameters or matrices which will decide what kind of photo detector it is, or how good a photo detector, how bad a photo detector is. Just like in solar cell you had open circuit voltage, short circuit current, fill factor, efficiency. Similarly in photo detectors you have certain things. As of now you think of photo detector as a black box because it can be a PN junction, it may not be a PN junction, it can be a Schottky junction, it could be an undoped film, it could be a doped film, it can be anything. So it's a photo detector, I'll call it PD. So essentially you are having light that is falling up of appropriate wavelength corresponding to the band gap, and you are going to get electricity, some very small electricity. Okay, you will probably bias it or you will maybe not bias it. Okay, depends. Okay, so if you, there can be photo detectors which could be sort of PN junctions in such that, so in unbiased, in a dark condition when you don't shine any light, you have a characteristic like this that I keep drawing, the forward bias. When you shine light, then it becomes something like this, right. I told you solar cell is operated in this fourth quadrant because you want to get power out of it like a battery. At this point, of course, you have no voltage applied, but you have good amount of current which we call as photo current or short circuit current. Here we will call it photo current only. A photo detector like a PN junction can be operated at this point definitely, or it can be slightly operated in this regime also. Slightly you apply negative bias, okay, maybe -2 volt, -5 volt. So you will get some, this current that you have here is actually the photo current, right. It's called photo current, and this current that you had in the absence of light you call it dark current, right. So one of the important parameters is photo to dark current ratio, I photo by I dark at a particular voltage, maybe -2 volt or -5 volt, whatever. This photo to dark current ratio should be very high. You want that ratio to be many orders of magnitude, so that you know your detector is more sensitive. If your photo current is very is almost the same as dark current, then it's not sensitive, right. There will be noise and other things. We'll come to noise and other things very quickly. So this is only a PN junction, but it may not be a PN junction also. It could be a photo detector, could be also, you know, such undoped silicon, for example. This is silicon which is undoped everywhere. So I am connecting I am connecting a voltage. Here you cannot get light if you shine, if you cannot get electricity just by shining light, because it's just undoped intrinsic silicon, maybe even slightly n-type doped silicon is not a problem, but you have to apply a voltage. Why? Because if you don't apply a voltage, if you just shine light here, light of appropriate wavelength which can be absorbed by silicon of course, and you want to see the current, you will not get any current. That is because if it is a uniform illumination, electron hole pairs will be created everywhere, electron hole pairs will be created everywhere. Now the problem is there is no internal electric field here, unlike in PN junction. In PN junction you have an internal electric field that sweeps away, but here there is no electric field, there is no junction, PN junction. So where will if there is no field, then there will be nothing to sweep the electrons and holes away to contribute electricity. Also the diffusion will be the same because everywhere the uniform electron hole pairs are generating uniformly, there is no diffusion, there is no concentration gradient, right. So in other words, you will not get electricity out just by shining light, you have to apply voltage. Okay. So this kind of detectors also there, these are called photoconductive detectors, we shall definitely come to that. So if you apply a small voltage, for example, if you apply some voltage and there is suppose no light falling, it is a dark condition, you are applying some voltage, this is I, this is V for example, and suppose I am making an ohmic contact to this silicon somehow, then if I am not applying any shining any light, I am just applying a voltage, I will get a current, sorry, I will get a IV like this. Okay. So this is current, say microamp, maybe some voltage or milliamp, whatever. The moment I shine light, there will be excess carriers that will generate now. There will be excess carriers that will generate. Now because you are applying a field, a voltage, this field will sweep away these excess carriers. This field will sweep away the excess carriers which were not there before. Before it was only intrinsic carrier concentration. Now it is excess carriers have come in the semiconductor because of the light shining, which can be swept away by the externally applied field. So your current will increase. You see, at any volt, say 1 volt, initially your current was this, again now your current has increased. Similarly symmetric, at -1 volt you have a current in dark current here, photo current is here. Even here you want a photo dark current ratio to be very high, which means this should be ideally very, like a insulating film, so that the dark current is very low. When you shine light you get a lot of current, so that is called photo current. The photo current should be very high compared to dark current, but this is symmetric. In a PN junction IV is not symmetric, but in this kind of photoconductor detector, this is called photoconductor detector, it is actually symmetric. Okay. So in any way, depending on the architecture of the device, whether it is PN junction or photoconductor detector sort of thing, you will have different kinds of IV, but the basic figures of merit that I am going to discuss now will remain more or less same. Okay, the figures of merit will remain the same. So one of them is the photo to dark ratio that I keep talking about. Now let us come more systematically about the figures of merit. I will call them figures of merit. Okay. So the first figure of merit is actually external quantum efficiency. Apart from photo to dark current ratio that photo to dark current ratio should be very high, that is important to know, but a figure of merit would be external quantum efficiency. External quantum efficiency is essentially, so you have this, whatever you have, photo detector, PN junction, non-PN junction, whatever, you are shining light, you are getting electricity. This electricity may be because of a bias voltage or maybe because of inbuilt field like PN junction, does not matter. You will get some electricity out. The question is how many electron hole pairs you are getting out per unit time. So how many electron hole pairs you are getting out of the circuit per unit second or per unit time. Okay. How many electron hole pairs are you are getting out divided by how many photons you are shining per unit time, per unit second. Okay. You are shining some photons, no light. So how many photons are falling on this sample per unit time, and the ratio of how many electron hole pairs are essentially coming out divided by how many photons are actually falling here. The active region will be here. I understand the active region is inside. The thing is that not all photons will probably reach the active region, some will get scattered, bounced off, so that is a different thing. And once the photons reach the active region, they will generate electron hole pair. So number of electron hole pairs that are generated in the active region, the number of electron hole pairs that are generated in the active region divided by the number of photons that are absorbed in the active region is IQE, that is the internal. So suppose you have a PN junction, I am just telling you, okay, this is the depletion region, you are shining light, some of the photons will get wasted in the neutral region, I told you, and only a fraction will reach the depletion region, which is the active region. So how many photons have reached here in the active region? Okay, and whatever, suppose 100 photons have reached here. Out of the 100 photons that have reached here, how many of them are actually leading to the generation of electron hole pair? Suppose 95 of the photons are successful in generating 95 pairs of electrons and holes in the active region. That's why then IQ will be called 95%, because 95% of the photons that are absorbed in the active region are actually converting themselves into electron hole pairs. But remember, not all the photons that you are shining here may be able to reach the active region. Some will get blocked, some will get absorbed here, reflected. There will be metal contacts, that metal contacts also will reflect and other things. So, not all fraction will reach here. Maybe you are shining 200 photons per unit time, only 100 reached the center here, right. And out of this 100 that reached, 95 of them got converted to electron hole pairs because of the, of course, when the photon gets absorbed at the same appropriate energy, your semiconductor will be such that electron hole pairs will be generated. So, you are generating 95% of IQE, internal quantum efficiency, but all the 95 photons that are all the 95 pairs of electron holes that are there may not be able to come out through the circuit. Some of them, the electron hole pairs might be lost here, some of the electron hole pairs will lead to extra parasitic drop here. So, the number of electron hole pairs that are coming out, of the circuit may be only 50 electron hole pairs per unit time are coming out of the circuit. So, the EQ will be defined as number of electron hole pairs that are coming out of the circuit, which is 50, okay, divided by the number of photons that you are shining per unit time, which is 200, right. That is 200, right. So, it will be around 25%. In this particular example, the EQ is 25%, okay, the external quantum efficiency, okay, but the IQ is 95%. You see, can you see the difference now? External quantum efficiency is 25%, but internal quantum efficiency is 95%, because internal quantum efficiency tells you how many electron hole pairs are generated at the active region divided by how many photons are absorbed in the active region. But external quantum efficiency says how many electron pairs hole pairs have come out of the circuit divided by how many photons are falling onto the device. So, there is a difference, because there is a losses in between and other things, right. So, now if you suppose you have a photo detector like that, you are shining light, okay, and the current that is coming out in the circuit, the current that is coming out, there is a circuit here, whatever, the current that is coming out is suppose I photon. So, the number of electron hole pairs coming out per unit time will be actually I photon by the charge of an electron. You agree? If there is a microamp of current, then 1 microamp divided by 1.6 × 10⁻19 coulomb will give you the number of electron hole pairs per unit time coming out of the circuit. You can do that. If your current photo current is 1 microamp, you divide it by 1.6 × 10⁻19 coulomb. Okay, ampere is actually coulomb per second. So, you will get number of photons, it will be probably like 10 to the power 13 or 10 to the power 12 electron hole pairs per unit second. Okay, I am just telling you. Okay, and basically you are shining light of some energy, POP, that is called optical power density, it is watt per centimeter square or whatever. Okay, so you are shining some light there, and you are shining a light of monochromatic wavelength, which means there is only one wavelength of the light. Your light does not have multiple wavelength, otherwise it becomes difficult. Okay, anyways, in photo detectors there is not a spectra of sunlight to detect. A photo detector essentially will detect a wavelength of a light of a particular wavelength only. That is the idea. So, you want to basically have a light that has a particular wavelength of lambda. Then the number of photons per unit time that is shining on the device is the optical power divided by hc by lambda. Hc by lambda is the energy of each photon. POP is the total power. So, if you divide that by hc by lambda, you will get the number of photons per unit time. You can do the math. Suppose you are shining 1 milliwatt of optical power, and the wavelength of light is suppose red. So, hc by red is 650 nanometer. If you do that, you will find out a large number. That number is basically number of photons per unit time. Okay. So, if I come to the next slide here, and I will show you what I mean. So, EQE, this is a figure of merit, by the way, that is why I am telling you, EQE is actually the total photocurrent by the charge of an electron divided by the total optical power by hc by lambda. What it will become is that I photon photocurrent divided by optical power into hc by q lambda. Okay. This is your external quantum efficiency. This is a very important property, this is a very important figure of merit for your photo detector. And I told you that external quantum efficiency, I will call it NE QE, actually is internal quantum efficiency times the efficiency that is limited because of collection. not all the not all the photons, not all the electron hole pairs generated in this device can come out. I told you some of them will go waste and get lost, and heat dissipation and other things. So that efficiency also reduces. So internal quantum efficiency was 95%. Remember, with that you have to multiply the efficiency of the collection into efficiency of transmission, because all the photons that you are shining may not reach the active region. Some of that might get lost in the neutral region, some of them might be bounced off from the metal contact and so on, right. So this is your expression for external quantum efficiency, but you have to remember that it is connected very much to the second most important figure of merit, which is called responsivity, and this is a very critical figure of merit for photodetector. Responsivity in a way is defined as how much photocurrent you are getting out of the device in ampere or milliampere whatever, divided by how much optical power you are shining, how much optical power, watt or whatever. So it's basically ampere per watt. The unit is ampere per watt. So how much of optical power you are shining at a particular wavelength, and how much current you are getting out of that because of that light you are shining. Okay, and this is definitely the photocurrent that you are measuring divided by input optical power that you are giving, and this responsivity is represented by a symbol of like stylish R. Okay, so essentially how much photocurrent you are getting divided by what is the optical power you are giving. This is very important. If you recall, this quantity in external efficiency is actually this responsivity. So then can I write this, that EQE is basically responsivity into HC by Q lambda. This is equal to your EQE efficiency. Can I write that? I can write that, right. So let me write here. So responsivity into HC by Q lambda equal to external quantum efficiency. If I assume that the external quantum efficiency is 100%, just hypothetically assuming that is the best you can get, then this is 1, that means 100%. Then your responsivity is given by Q lambda by HC. This is amp per watt. Okay. What does it mean? It means the responsivity of a photodetector. This is the theoretical limit. Sorry, this is the theoretical limit to responsivity. Okay, of a photodetector. This is the theoretical limit of a responsivity photodetector. Surprisingly, this depends on lambda, which means if I use a UV light, if I talk about a UV detector of 300 nanometer wavelength, then whatever responsivity I get, okay, and compare that with an infrared detector I am using of wavelength suppose 1500 nanometer, then the responsivity, the theoretical responsivity for UV will be almost, here it is lambda directly proportional, no, 5 times less than the responsivity at infrared. I mean, here it is 300 and 1500, it can be anything, it can be 300, 3000, whatever I am just talking about. Okay, what I am trying to say is that the theoretical limit to responsivity in amp per watt is dependent on lambda. So if I use a UV light, which means a short wavelength, my responsivity also will be low theoretically. If I use an infrared light of a higher wavelength like 1500 nanometer, 2 micron, 3 micron and so on, then the responsivity also will be theoretically high, which means the theoretically achievable maximum responsivity in amp per watt, if I plot with respect to lambda, then it will be like a linear plot. This is say 200 nanometer, I am just saying this is 2000 nanometer, 2 micron, it can go to much higher, 3 micron, 4 micron, I am just giving you a range. So you see, red will have higher responsivity than green, green will have higher than blue, blue will have higher than UV will have very low, red will have higher here, infrared will have even more higher. So theoretical responsivity will be high, and you can actually calculate the value here. You can plug in the value HC by lambda, this thing QHC by lambda. For example, if you have around 250 nanometer, I know the value, it is around 0.2 amp per watt. Okay, at 500 nanometer wavelength, it will probably be around 0.4 amp per watt. Okay, at 1 micron, which is almost silicon band gap, you will have probably like 0.9 amp per watt, right. So many and so. So the actual responsivity is actually increasing, the theoretical limit to responsivity increases with wavelength. This doesn't mean that your UV detectors will always have lower, this will always have lower spectral responsivity than IR. It doesn't mean that you should not work at lower wavelength. That is not the point. The point is that if I use do you know what is the physical reason behind this, by the way? Why is that this is coming out like that? And responsivity is a very important parameter of photodetector. It's because if you take one photon of IR infrared, say I'll talk about say 1500 nanometer wavelength photon. When if it is absorbed in a material completely, it can give rise to one electron hole pair, right. Similarly, one UV photon which is say 300 nanometer, one single photon, if it absorbs completely, it also gives one electron hole pair. No discrimination here. One IR photon will also give one electron hole pair, best case. One UV photon also will give one electron hole pair, best case. Now, if I take 1 watt of power, optical power, 1 watt of optical power in IR, okay, 1 watt of optical power in IR, and then I take separately 1 watt of optical power in UV. Because the UV photons have more energy, hc by lambda, where lambda is 300 nanometer, this photon has more energy than an IR photon, hc by lambda, lambda is 1500 nanometer, right. So this IR photon has lower energy, one photon has lower energy than UV one photon. So same power, 1 watt, if you find out how many IR photons are there in 1 watt, the number will be more compared to how many UV photons are there in 1 watt. You see my point? 1 watt is fixed, but the number of photons that can be accommodated in 1 watt is more in IR than in UV, because IR photon energy is less. It's like you have only a fixed amount of 1 watt. You can think of a one fixed volume in one fixed trunk of box. The volume is fixed. Now you can either fit in only few footballs, or you can fill in many small marbles, because the size of each marble is small, the size of each football is large, but the volume of the trunk is fixed. So 1 watt is fixed, but the number of IR photons will be more than the number of UV photons there, and 1 photon gives you 1 electron hole pair. That's why more IR photons in 1 watt means that you will get more electricity out of 1 watt of IR power than in 1 watt of UV power, and that's why spectral responsivity goes as Q lambda by Hc amp per watt for 100% efficiency. Okay, but this is the theoretical limit. In some cases there can be an internal gain in the device. If there is an internal gain, then your responsivity will be multiplied by the gain. The gain can come because of many factors, avalanche or many other traps and other things, don't worry about that, but there can be a gain, and efficiency of a photodetector can be more than 100%, which means the responsivity can be more than the theoretical limit. Why is that possible? There can be gain, there are physics behind it, there can be gain, okay, trap related gain and other things. Let's not come to that so much now, but please understand that. So 2 figures of merit we have discussed. These are important figures of merit for photodetector. We'll need them actually, that's why I'm talking about them here in details. One figure of merit is called bandwidth. So bandwidth is essentially represented by B, and it's basically speed, how many gigahertz or megahertz the device can work at. When I say gigahertz and megahertz, I do not mean the optical signal. The optical signal red, blue, green is not gigahertz or something, they are thousands of terahertz or something, the optical signal. This gigahertz or megahertz, this bandwidth basically means how fast the device can operate. Okay, and so with respect to this also another quantity is related, actually both of them in a way, that is called transient response. Essentially both of them tell you how fast your photodetector is, how fast your photodetector works. I'll come to that. So essentially what means is that if you have a photodetector, okay, and you are putting a light signal, input light signal, suppose this is time axis, suppose the input light signal is 0, suddenly you switch on the light, and you kept the light on for maybe whatever time, then you switch off the light abruptly and go. Now this is the input. Now output of the photodetector has to give an electricity. This is input optical power, but the output has to be electricity, I photon. So this is time. At this time and at this time, the photodetector will not give the electricity abruptly. It will take some time to rise, then it will be there, and once you switch off the light, it will again take some time to fall off. So that speed at which it can operate, how abruptly can it turn on and off, that is basically the speed at which that determines the bandwidth also. Now if this time scale is in the range of seconds, then of course photodetector is very slow, it can operate, and of course, but it is in the case of nanosecond. If you are turning on and off the light in 1 nanosecond, can the photocurrent rise to the, this is the dark current, this is the photocurrent, can the photodetector's current rise from dark current to photocurrent in 1 nanosecond and again come back in 1 nanosecond or 1 picosecond, 1 microsecond? That determines the speed and the bandwidth of the device. The bandwidth will be inversely proportional to that, right? So if it can actually go in 1 nanosecond, turn on and off, then you say it's very fast detector, its bandwidth is so high. And if it cannot, then you know it's slow. I mean, depends on what time you're putting in, millisecond, microsecond and so on, okay. So essentially what you do is that the way we define is that if this is your photocurrent, then there's a 90% of the photocurrent is here, okay, and this is the dark current. This dark current is not 0 by the way, it will be very small like picoamps or femtoamps. You take 10% of this value here, this is 10%. What is the time that the detector takes for it to rise from 10% of the value of photocurrent to the 90% of the value of the photocurrent? That time is called the rise time. Similarly, this is 90% of the peak value, this is 10% of the peak value. How much time does it take to come from 90% to 10% is called the fall time. So these are called rise time and fall time of the detectors. If the rise time and fall times are very small, very nanosecond or whatever, you say detector is very fast. If it takes a long time, then you know that it's small. It's very slow. For example, it may be so happen that this is time you have switched on and off the device. Sorry, let me do that again. You have switched on and off the device, but your photodetector may not be able to respond only. At this point, it slowly increased to rise. It didn't even reach the value. It was rising. Then you switched off, it again fell slowly. Takes so much time. It couldn't even rise to its value completely. This is a slow detector. But again, it depends on the time scale. Are you talking about millisecond? Are you talking about nanosecond? Whatever, that depends. If it is working like this in nanosecond, maybe in millisecond it will be fast. So it depends on that way, okay. So that bandwidth is basically up to what frequency of modulation of this signal. You see, this signal can be modulated, the input optical signal can be modulated at some frequency. It's not the, please remember, this is not the frequency of the light. Light is infrared or red or violet, whatever, that is like thousands of terahertz probably. That is not the frequency of light I'm talking about. I'm talking about light on and off, on and off, on and off. This is called modulation frequency, okay. You are modulating the light on and off in certain speed or frequency. This is, can the photodetector's photocurrent also follow this signal on and off as fast as the light signal? That represents the bandwidth or the speed of the photodetector, okay. Because, and this is important because this on and off, these are actually used in frequency modulation, amplitude modulation sort of thing, signal processing in optics, fiber optics cable. The way you get internet data in your home from fiber optic cable is because of this, by the way. Infrared light is sent through silica fiber, that fiber optic silica core. That actually on and off is modulated. On is, suppose this is a digital 1, this is a digital 0, 1, 0, like that, right? So you have to send a signal. That means there has to be a light source like an LED or laser diode which can on and off very fast. So 0, 1, 0, 1, whatever. On the detector side of the fiber optic also you need a detector, a photodetector in infrared that will be able to respond to that so fast, on and off. Only then you will be able to get all the digital data, right, which constitutes your internet, your Facebook, everything, right? And your internet in fiber optic cable, if it works at a speed of 1 Gbps, it means 10 to the power 9 bytes. 10 to the power 9 bytes per second are coming to you. Actually 10 to the power 9 bytes means that 10 to the power 9 times your light has to switch on and off per in 1 second. Please remember that 10 to the power 9 times your light has to signal on and off in 1 second. Your detector that you have on the other end of the fiber optic should be able to respond to 10 to the power 9 or 1 billion. The light that your optical fiber cable is detecting, the light that is coming is changing 1 billion times in 1 second. Your photodetector should be able to respond to that 1 billion times a second. Otherwise your internet will not work. Otherwise you will not be able to get the data, okay, your broadband data. Your light will be on and off 1 billion times. Your photocurrent should be able to respond to that. Your photodetector should be able to respond to that as fast as you can, as fast as the light comes. Only then you will be able to reproduce your data, right? That is true, right? So that is true. So this is about the speed and bandwidth, and there are other things also with respect to speed and bandwidth. So what we will do is that we will end the class here today. We have discussed enough of photodetectors for today's class. We have introduced the concept of photodetectors and different kinds can be there. I told you what are the basic differences with solar cell. I introduced some of the concepts of figures of merit, efficiency, spectral response, bandwidth, transient time. There's a lot more things to do. We'll not go into much depth, but we should be aware and familiar with the basic terminologies, basic working. So what we'll do in the next class is that we'll continue with the figures of merit. I'll talk about a little bit about more of transient response, noise, and detectivity. Specific detectivity is very important. All these things are figures of merit, and after that we'll be discussing some sample cases of photoconductive detectors, PN junction detectors, what is the speed, what is the responsivity, and so on, so that we can understand the working of photodetectors. Okay, so we'll end the class here today. Thank you.